Hello and welcome back. Unfortunately, I have to take a family member to the doctor's office today for an appointment, and I may not make it back in time for lab. So I made this video just in case so that you have the pre-lab information that you need so you can do the lab and get through it without any trouble. So I'm available for questions. If you have any questions, feel free to send an email. Check out the materials I posted on the webpage. Rewatch the video if you need to. All of those options are available. Feel free to contact me. I will be available via email though. So what is today's lab about? Today's lab is about optics, or the study of light. And here's a mind-blowing thing that's just it's crazy. The only thing that we see in the entire universe is light. I mean, I might think I can see that bookshelf back there, but I don't actually see that bookshelf. What I see is the light bouncing off of that bookshelf. And I know that's true because if I turn all the lights off, if I take out all the light, the bookshelf is still going to be over there, but I won't be able to see it. So it's not the thing that we see, it's the light bouncing off of that thing. And since light is the primary means for us as human beings to interact with the world and to take in information about the universe, we've been studying it for a long time. The study of light, optics, falls into two main categories. We have our physical optics, where we have light considered as a wave, and we have geometric optics, where light is considered a particle. This week, we're going to be talking about geometric optics. Next week, we'll talk about physical optics. That's a little bit reversed from what's on the plan. It made more sense to do it in this order. So that's what we'll be talking about today. Geometric optics, light considered as a particle. And essentially, we're going to be discussing the options light has when it interacts with matter. When light interacts, it's not like it chooses, but there's three things that happens when light interacts with matter. Either it's going to get absorbed by that matter, and when light shines through something or shines on something, it warms up a little bit. So that's energy getting absorbed. It might reflect off. Like I said, there's light reflecting off of that bookshelf. There's light reflecting off of my red shirt. There's light reflecting off of me that you can see. So when light interacts with matter, it reflects. It could also pass through. Some light actually does pass through things, like the window over there, this magnifying glass. So light can absorb, get reflected, or bend as it goes through, passes through. When it bends, we call that refraction. So those are the two that we're actually going to be talking about today mostly. Reflection, refraction, the bouncing or the bending of light. So today's lab is going to involve a couple things. This video, I'm going to talk to you about optics. First of all, I know you're not getting a lot of optics just because of the circumstances. We didn't get as far in physics as we had hoped. There will be an optics course that I will be teaching, and it's a really fun course. So if you're a physics minor, physics major, or you're just interested in really cool stuff, I highly recommend taking the optics course that's offered. It's an upper level physics course, but it's very hands-on. It's project-based. You're going to be building and designing microscopes. So I recommend it if you have an opening and you're looking for a really cool class to take. I highly recommend taking the optics class. We'll cover this stuff that we're talking about today and next week in a lot more depth, and you'll be putting it to use where you're actually going to be building and designing microscopes. You're going to be building optical systems. You're going to be using lasers, which is all pretty cool. So, but that's beyond the scope of today. That's in the future. What are we going to do today? So this video, first of all, you're going to watch this video, and I'm going to tell you about the labs. I'm going to explain geometric optics to you, and my lab partner, Joey, and I will be demonstrating some of these ideas using the stuff I brought with me. Then I'll show you the labs, and then you'll get to work. So the labs today, there's two of them. One is drawing ray diagrams, which I'll show you how to do, and the other is using a simulation for geometric optics, specifically for lenses and mirrors. So that's what we're going to be doing today. I'm going to make me small and make my screen big. As per usual, you have your pre-lab and the pre-lab quiz. You also have post-lab posted. The labs themselves are going to be located down here in this folder, which right now at the time I'm filming this isn't available, but it'll be available to you soon. Certainly by the time you're watching this, you'll be able to access that folder and get into your 2 labs. The pre-lab materials look something like this. We've got videos on geometric optics here, quick lessons. We've got some text over here about lenses. Those are 2 different types of lenses, and mirrors, 2 different types of mirrors. This is an entire lecture on the topic, since you aren't getting that just yet in the lecture here. So if you want more information, it is really interesting stuff. That's a pretty decent lecture. Here's a video on ray diagrams. So if that part of this lesson doesn't really come through, if you need a little bit of extra help with ray diagrams, here's ray diagrams for mirrors, and here's ray diagrams for lenses. And maybe the strategies are slightly different between what I'm going to show you and what the guy in the video shows you, but they're going to be similar enough that you'll get the idea. And again, terminology over here, if that part, if there's something you're not sure of, if I'm going through too fast in the video, if it's just not making sense, then this is a good resource for you. Okay. And the simulations, we'll get to those in a couple of minutes. There's some really cool ones in here I want to show you. But first of all, let's look at this one. This is a Phet simulation where we have air up here and a laser pointer that I can move the laser pointer around, and we have water down here. I can actually make it something else. I can make it into glass or some mystery material, but we'll leave it as water for now. And when I hit that button, we see that the laser beam, laser is an acronym, I don't know if you knew this, light amplification spectrum emission radiation. Laser, L in laser stands for light because that's what it is. It's just concentrated light of a single frequency. Okay, so the laser light comes in, it hits the water. We know that light travels through water because water is clear. We can see through it usually. Sometimes Lake Erie is not super clear, but sometimes it is. You can see through it just fine. Some of the light hits and bounces off. It reflects. Some of it gets absorbed, but we're not really concerned with that today. We're not really looking at the absorption. And some of it hits and passes through. And we notice that the direction of the light, it actually changes a little bit. It wants to keep going in a straight line, but it bends as it goes from one material to the other. That's called refraction. We'll talk about those 2, reflection and refraction today. And we can figure out what these angles are going to be based on the physical laws that we're going to talk about today. So the law of reflection, we're going to start with reflection. The law of reflection says that whatever the angle of incidence is will equal the angle of reflection. Now, that's just a fancy way. If you're a pool player, like billiards, if you've ever played pool before, then you're probably familiar with this law. And what it says is that whatever the incoming angle is, it's going to equal the outgoing angle for reflected light. And we can see that with the simulation. As I move this, if I put this at the 60 mark, it's going to go out at the 60 mark. And very appropriately, the angle is being measured from this up and down line right here, that vertical line. That is the normal to the surface, the perpendicular line to the surface. When I'm measuring these angles for the law of reflection, I'm measuring them from the normal. So this 60 degrees will equal this 60 degrees. It's a tempting mistake to look at this 30 degrees and call that the angle of incidence, but that's not the one we're talking about. For the purposes of our calculations, it's the angle from the normal. So don't forget that. That's important. Okay, I'm going to jump off of my screen sharing right now and go into some demos with Joey. So it'll be a couple seconds for me, but it's going to be immediate for you because I'm going to edit them together. All right, we're here with, I've got some lasers. So I've got a bluish, purplish laser there, and Joey's got a red one. The green laser's falling apart a little bit, so we might not use that one too much, but let's see if I can get it to actually turn on. Oh, there it goes. It's actually pretty bright. So we've got 3 lasers, and we've got a mirrored surface right here. And Joey, if you're going to shine the light at the edge of the mirrored surface, if I hold the camera right above, you can see that the angle of the incoming light ray and the angle of the outgoing reflected ray compared to the normal is going to be the same. You can even pause the video, get a protractor out, and measure it if you want. It's going to be the same. It's the law of reflection. If I shine the purple light in, you get the same deal. The incoming light beam makes an angle. The outgoing reflected ray is going to make that same angle. The angle of reflection equals the angle of incidence. Angle of incidence is the angle that's incoming, angle of reflection is the outgoing. And that's true for any smooth surface. You're going to have, it's actually true for any surfaces, but we're going to get into that in a minute. So that's true for any smooth surface. You're going to get that cohesive beam of light coming out. So I've got my iPad here. Joey, you want to hold the camera? All right. And I dropped the laser, so grab this one. I've got the light hitting the screen, and it's going to come out at an angle. I've got a single dot on the screen. I've got a single dot on the board.
That small dot's just the reflection from the board, not the reflection from the light.
So you got the dot on the screen, you got the dot on the board right there. We call that specular reflection when it's a smooth surface and, oh, hey, and the outgoing light beam is reflected at the same angle because the normal doesn't change. I'm going to explain that a little bit more, but I want to show you the opposite of that. That's if you have a smooth surface. What if I have a rough surface? Now, paper might seem smooth, but if you zoom in on it close enough, it's made out of all these fibers, wood fibers. You won't be able to see it zooming in like that, but if you had a microscope, you could. And if you don't believe me, put some paper under a microscope. It's woven together fibers made out of wood, which is not as smooth as it might initially appear. This is also the reason why you can write on paper and I can see it from all different directions, as opposed to if I had a mirror on the table, everybody looking at it from different directions would see something different. But this is diffuse reflection, where I shine the light on the board, on the paper, and the reflection on the board. Now you see the dot on the paper, but on the board you see kind of a ball of light, a blob of red light that's reflected down.
Instead of the exact laser.
Yep, instead of the single point of the laser. Exactly, Joey. So that's called diffuse reflection. And I'll talk a little bit more about that on my iPad, so stay tuned. Okay, I'm back, and we have specular versus diffuse reflection, which I just tried to show you with Joey. I'm hoping it came through in the video, but I can't really tell at this point as I'm recording it. But just in case it didn't, with specular reflection, we have a smooth surface, and we have incoming light rays that are all coming in parallel to each other. And they all obey the law of reflection. So if we have the normal to the surface, there's a normal, there's a normal, there's a normal. The incoming light rays are going to bounce off, and they're going to keep the same angle, and they're going to leave parallel, just like they entered. They came in parallel, they leave parallel. Now, it looks like those are spreading out, but that's just because I'm drawing with a stylus, and it's not as precise as if I was drawing with a pen or a marker on the board. But the incoming light rays go in all parallel and all at the same angle. They come out all parallel and all at the same angle, because the law of reflection says compared to the normal. That's how it works. That's how it's always going to work. They're always going to have the same angle of incidence as they have angle of reflection. So with diffuse reflection, does that mean, since it's diffusing the light out, does that mean that the law of reflection isn't obeyed? No, the law of reflection is still obeyed. The problem is, when you have a rough surface, the perpendicular to the surface at one spot isn't going to be the same as the perpendicular to the surface at other spots. If I draw lines perpendicular to the surface on this rough surface, those perpendicular lines are not parallel to each other because the surface is rough. So an incoming light ray that hits here is going to follow the law of reflection for that spot. And that same incoming light ray coming in here is going to have an angle of reflection that's going to be much different. Incoming light ray coming in here is going to bounce off like this. So the outgoing light rays are going to go at different angles. So light that's bouncing off of this rough surface, some of them are going to go this way, and some of them are going to go this way, and some of them are going to come back up this way. So it's going to spread out, go in different directions. It's going to diffuse out, hence the diffuse reflection. It's still obeying the law of reflection, but it's not giving you that cohesive beam like you get with specular reflection. This is why you can see an image of yourself in a mirror or in a blank computer screen or in my iPad when it's turned off, when it's not backlit, because it's a smooth surface
and the light rays coming in are going to be coming out cohesively and provide that image for you. It's also why if you're looking, let's say we put a mirror on the table and you're sitting on one side of the table, I'm sitting on the other side, and somebody else is sitting like across, and somebody's sitting at all four sides of the table. Each person is going to see something different than the other person across from them because the angle is going to be different for each person. If we put a piece of paper on the table right in front of us, though, we can all see the same writing because those reflections from the writing are going to be going in all different directions. So I can see your paper that you're writing on from the other side of the desk, and it looks the same to me because the light that's hitting it is diffusing out in all directions.
So we've been talking about what happens to light when it hits matter, and one of the things that can happen is it bounces off. Just like if I took a ball and threw it against the wall, like when I'm playing pool and I hit the ball against the edge of the pool table, it's going to bounce off with the exact same angle that it came in at. That's the law of reflection. But what happens when light passes through something? I know light can pass through stuff. I have a window right over here. There's light passing through the window. I can see it. I have this glass cube right here, and there's light passing through it. You can see through the cube. I've got a magnifying glass here, and there's light passing through the magnifying glass. Piece of plastic, clear plastic, light's passing through that clear plastic. So what happens when light passes through a translucent substance? Well, interesting stuff happens. And it follows a similar pattern to what happens when particles enter into a new substance. So let's say I've got a golf ball. I take my golf ball and I throw it, and it's moving along at some direction, and it hits some water. So I throw it into a pond. I hit it into a pond, whatever. So it's going at this angle to the pond here. It hits the pond and it slows down so suddenly, and boom, it goes at a different angle than it was going before. It was going this way, and then suddenly it's going more straight down because it slows down. It's similar. A good analogy that we like to use in our physics textbooks is if you are pushing a lawnmower and you're pushing it down a sidewalk to go from one spot to another, but the edge of the lawnmower, the front right wheel of the lawnmower goes off of the edge of the sidewalk into like sand or into some grass. Well, it can't go as fast through the sand or grass, and that causes the lawnmower to change directions. When we weren't quarantined, you're out at the store, you're pushing a cart, a little stone gets caught in the shopping cart wheel, and it causes the cart to veer to the side because the wheel changed speed. A change in speed causes a change in direction. So light, even though the speed of light is a constant when in a vacuum, it moves at different speeds when it's moving through different media. So when it moves through air, it's pretty close to the same as the speed of light in a vacuum, so much so that we actually round it to be the same thing. But when it's moving through water, it's moving significantly slower than it was. And the ratio of those speeds, the ratio of the speed of light in the vacuum compared to the speed of light in the medium. So when we're talking about speed of light in a vacuum, we use the symbol lowercase c. That's the speed of light in a vacuum divided by the velocity of light in the medium. That ratio is called the index of refraction, n. And it's going to help us determine the change in direction. I don't know, actually, you can see that. It's big on my screen, but just so you can see it. Okay, so there, now I'm the bigger part of the screen. The index of refraction is the ratio of the speed of light in a vacuum to the speed of light in a material. That change in speed will determine how much angle we get in our change due to that change in speed. So let's go back to that simulation. So I'm going from air into the water, and the light is going to slow down. The incoming light is 30 degrees from the normal, and the outgoing light is less than 30 degrees from the normal. Why? Because the light slowed down. And when the light slows down, it bends towards the normal every single time. My mnemonic for this is up, up, and away, down, down to the ground. It sounds silly, but it helps me remember. When light speeds up, so let's say it's going from water into air, now it's speeding up because it's moving slower in the water and faster in the air, and it's going to bend away from the normal. So speed up, 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 and away. If it's going the other way, if it's slowing down, down, down to the ground. So it's my Superman mnemonic. The light that is speeding up is coming from 30 degrees and it's going to leave at an angle greater than 30 degrees. To figure out what that angle is, I'm going to erase my board. We use something called Snell's law. So again, I'm going to zoom myself in here. Snell's law equates those angles with that change in speed. So Snell's law looks something like this. N1 sine theta 1 equals N2 sine theta 2. All right, N1 sine theta 1 equals N2 sine theta 2. The index refraction of the first material times the sine of the incoming angle equals the index of refraction of the second material that you're moving into times the sine of the outgoing angle. Snell's law it's actually an extension of the law of reflection. Actually, if you get into the math and the derivation of that, it comes from the same place as the law of reflection, but it's really handy. So it's actually why lenses work the way they do. So we'll get into that. But first, I want to call Joey back in here and show you some examples of that. Okay, so we just talked about Snell's law. Let's see it in action. So Joey, come here. Let me show you. So I've got my laser beam right here, and I'm shining it on the paper, and it wants to go through straight line right to the tip of that spoon there. But when I put this block of glass in the middle, see how the laser comes over here? It's not hitting the end of the spoon anymore. It's been shifted over at least a centimeter because the light coming in is going to slow down, bend towards the normal. It wants to keep going this way. Can you see my finger on there? So it wants to keep going this way, but it doesn't. It slows down and bends towards the normal. And then it speeds up when it leaves the glass. It bends back away from the normal, but it's been shifted about a centimeter over. Pretty cool, right? The same thing happens. I've got this little container full of glass, and it's got a shift just like before. It's going to be a different amount of shift than with the glass block because this is full of water. So water has a different index of refraction than the glass did. Try to hold that steady, buddy, right on there. It's cool looking, right? We can see the reflections over here. Every boundary, we're going to get both reflection and refraction. But we see it bend a different amount than, now this is a plastic block, and it's going to have a different amount as well, a different amount of shifting. I like this purplish bluish laser because it really shows the beam inside of the block. All right, that's Snell's law in action. Cool. Okay, so we've been talking about light interacting with flat boundaries, but what happens when we're dealing with like a curved surface, like a spherical lens or mirror? A good example that you probably have readily available to you is one of these. It's a spoon. So if I look at the spoon, the inside of the spoon with the bowl of the spoon kind of facing towards me and bowing away from me is called a concave surface. It's like a cave in a mountain where it's dipping into the mountain.
That's what I was just thinking.
Hey, good. Great minds think alike. And if you look at your image in there, it's going to be upside down. Your reflection is going to look upside down.
And it makes me look all curvy and tall.
Yeah, because it's not exactly a sphere. It's not a spherical lens exactly, but it's a good example to show you what's actually happening. Flip it over when the middle of it is a little closer to you than the edges, and you have a convex mirror. And you look right side up in that one. So,
and more hunched it looks.
So check that out. Now, I have an example right here. You can see. This is concave, and if I shine the light ray straight in, it's going to bend towards the central point, towards the axis in the middle. And no matter where I shine it in, it's always going to bend towards that middle. Is that showing up in the picture, in the video? Mm-hmm. Bends towards the middle, bends towards the middle. Always. And all of those light rays coming in parallel to the axis of this thing are going to converge at a single point, which we call the focal point. If I turn this, now I have a convex surface, like the backside of the spoon, and it's going to bend away from the middle point. See how it's always bending away, no matter where I point it? It's going to diverge away from a single spot, so it would have a negative focal length behind the mirror. Similar things happen when I have curved surfaces of glass with refraction. I'll show you in a diagram a little bit more of why this happens, but notice that wherever I shine my incoming light ray, it's going to bend towards the middle, towards the axis of this lens. And all of those converge at a single point on the far side, which we call the focal point. That's when the piece of glass is fatter on the middle and thinner on the edges. What if it's the opposite? What if it's fatter on the edges and thinner in the middle? Well, the opposite is going to happen. We get refraction in the opposite direction as it spreads out away from a central point. No matter where I'm putting, the light beam that passes through is going to spread out, is going to diverge, which means it never meets at a single focus point on this spot, but they all come from a single direction or a single point over here. We have a negative focal length, just like the convex mirror. So I'll show you a couple diagrams and how to find images due to these things. Okay, so there's a few different configurations we can have as we're designing optical instruments using these ideas of reflection and refraction. So one of them is where you have a mirrored surface that is bowed in like this, sort of an indentation where the edges of the mirror are closer to you and the middle of the mirror along the axis is farther away. This is called a concave mirror or a converging mirror because it causes light rays to converge on a single focal point, and we say it has a positive focal length because they actually converge at a single spot. They produce images that have either a positive or a negative image distance. That means the images either appear in front of or behind the mirror, which means they're either real or virtual. So this can have either real or virtual images produced at the same side of the mirror or the opposite side of the mirror. And they can have positive or negative magnifications. They can have upright or inverted. It can also make objects that are bigger or smaller, images that are bigger or smaller than the object, which means the objects could be closer than they appear because the image might be bigger or smaller. That's the image heights. They can be upright or inverted. If I have a mirror, a mirrored surface, where the middle of that mirrored surface is closer to me than the edges, I have a convex mirror, which has a negative focal length. It causes light rays to diverge from that central axis, that primary principal axis in the middle. It always produces virtual images, so it always has a negative image distance. The mirrored image will always be on the far side of the mirror. It will always be on the opposite side. It will always be upright, so it has a positive magnification and a positive height. Similarly, we can have lenses that are convex or concave. The convex lens looking like this with the middle of it being fatter than the edges has a positive focal length by the same logic we were using before. It's going to have very similar characteristics to that concave mirror up here. And a diverging mirror has the edges that are fatter than the middle. And it's going to be very similar to the convex mirror. This, by the way, is on the last page of the lab that's in your lab manual. So you can check this out. You have this in your lab manual.
So let's talk about what happens when we have incoming light rays coming in at angles. So remember, law of reflection, we have a mirror here. We have a mirror right here that is curved. It's kind of like looking at the inside of the spoon. The middle of the mirror is farther away, and we just said that that's called a concave mirror. So the light ray is going to come in, and let's say we shine a beam of light like this. So we have light rays coming in that are all parallel to that line down the middle. That line down the middle is called the principal axis for this lens. And this lens is called a spherical lens, because if you can imagine, we had this big round spherical ball of mirrored material, and we cut a little circle of it out. That's what would form this mirror. So the law of reflection says that the incoming light ray has an angle of incidence from the normal, and the normal in this case is going to be like this, and it'll have the same angle for the outgoing light ray. It's going to come out something like that. I'm freehand drawing these, but I think you get the idea. The normal here is going to be slightly different. It's going to be pointed a little bit more towards the middle. So we get a slightly different angle for this light ray coming off, and it's going to come out like that. The one that hits right in the middle on the primary axis, the principal axis, is going to bounce straight back. The two on the bottom are going to follow the same sort of logical steps as the ones up there on the top. And we'll get the same process, the same law of reflection, and it's going to come out with the same angle as that incoming light ray. And you should be noticing a pattern here. Those light rays are converging. Sometimes it's called a converging mirror. Concave or converging mirror. It's converging all at a single spot, which we call the focus. Okay, now we're looking at the opposite side of the mirror, I suppose. It's like you flip, I said before, you're looking at the inside of a spoon. Now you flip the spoon over and we're looking at the back of the spoon. Light rays are going to come in like they did before. So we got this set of parallel light rays coming in, parallel to the principal axis. And they're still obeying the law of reflection, except now the normal is going to be pointed out like this. The normal is going to be pointed out like this. The normal here is the axis, but here it's going to be pointed like this, and here it's going to be pointed more like that. Those are supposed to be straight lines. We're still obeying the law of reflection, but since the incoming light ray is coming in on this side, it's going to bounce out away like that, such that the angles are the same. Same kind of deal here. It's going to hit, it's going to bounce at some angle. This one's going to hit, and it's going to bounce straight back because it's along the normal. This one's going to hit, and it's going to bounce out like that. This one's going to hit, and it's going to bounce off like this. Now, those light rays are diverging away from each other. This is called a convex mirror, by the way. Convex mirror. Those light rays are going to diverge out. They are never going to cross because they're getting farther and farther and farther apart. So they're going to diverge. But our eye doesn't really process light as having bounced. It says light travels in a straight line. It always travels in a straight line. So if we were to look at this mirror, our eye would see this light ray and say, oh, that light ray didn't come from over here, wherever the source of the light is. It came from back here somewhere. I'm going to switch colors as I'm tracing these lines backwards. Switch it to green. Our eye, or our brain, interprets that light as coming from behind the mirror in a straight line from where that ray is coming from. Similarly, this one traces straight back. This one traces straight back. This one up on top is going to trace straight back. This one is going to trace straight back. And while they don't ever actually meet, they appear to meet at that one spot, which is the focal point. And it's at a distance behind the mirror, kind of the opposite of what we expect. So we attach a negative sign onto that and say it has a negative focal length. The focal length being the distance from the lens itself to the focal point.
So looking at the simulations that I've shared with you on my pre-lab site, we have the first one is the Phet Simulation. This is the one we're going to be using in the Phet lab. And we've got an object over here. It's a pencil, and it's in front of a converging lens. And you see that the distance to the image is found using three representative light rays coming off of the object. It's kind of neat. You can change the object. You can change the characteristics of the lens, but the image is located some distance away depending on where the object is and depending on what the focal length of that lens is. And I can even get a virtual image, which we'll talk more about all of these things. I'm actually going to show you some examples and show you how to draw some ray diagrams when I get back to my iPad. But that's the simulation we're going to be using. But I wanted to show you this one. This is probably my favorite one. It's also linked in the pre-lab page. But this is the one that gives you the most control and the most details. So I've got a light source, sort of like the top of that object, where if light is hitting this object, there's actually light going in every single direction. There are rays going out all over the place. We just pick three to represent that are easy to use, that we know the rules are going to follow, which I'll talk about, like I said, on my iPad. But this shows that there are light rays going in every direction, and they still will converge on that one single spot. And that spot is going to change depending on where the source is. So those are some simulations that you can play around with. This one is way cool, but maybe a little more detail than you need to get into. The other one is the one we're going to be using for the lab itself.
So now we have an object. That green arrow is just something that's sitting in the light, and it's reflecting light in all different directions. There's light going every single direction you can imagine. And some of that light is going to bounce off of that object and hit this concave mirror that I've drawn right here, that concave mirror. So some light is going to hit and bounce off of the top of it. Some of it's going to hit and bounce off of the bottom of it. We're going to choose 3 specific light rays that are bouncing off of that object and hitting that mirror that will help us to create a diagram that shows us at least a good approximation of where the image is going to be created by that mirror. So we're going to pick 3 light rays that are going to come off of the top of that arrow. So there's light hitting the top of that arrow and it's going in all different directions. So at least one of those light rays is going to hit and bounce off of that top of that arrow and travel parallel to the primary axis, parallel to the principal axis. And we know from previous diagrams and demonstrations that I've done that light that travels parallel to the principal axis is going to bounce off of that mirror and go through the focal point and then just continue on. Similarly, if I have light, and there's light going in every direction, so at least one light ray is going to hit the top of that arrow, and it's going to travel through the focal point and then hit the mirror. By the same geometry that we just did, so we said if light goes parallel to the primary axis and hits the mirror, it's going to go through the focal point. Well, if light goes through the focal point and hits the mirror, the law of reflection still is obeyed, and we know that angle has to put it parallel to the primary axis. So it's going to leave the mirror parallel to that axis. The last ray we're going to draw is going to go from the tip of the object, the top of the object, and it's going to hit the mirror right at the axis, right at the middle. And at that spot, the normal to the mirror is the axis. So it's going to bounce off with the exact same angle as it was coming in at. And it's going to go away from the mirror at that same angle. And that spot where those 3 rays cross, we've sort of triangulated the position of the image. I'm going to draw the image in blue, even though it would be the same color as the object. But I'm going to draw it in blue so you can see the difference. That will be the spot on the image that corresponds with the spot on the object we drew the rays from. So the image is going to be right there. Since I drew from the top of the object, where those 3 rays converge will be the top of the image. Now, a couple things to notice about this. Because this is a freehand drawing, we can't really measure the height to see if it's been magnified or not. Sometimes it's obvious. Sometimes the image is way bigger than the object or way smaller, so you can see if it's been magnified positively or reduced. But we can see right away that it's inverted. We can also see that it's a real image because these light rays are actually crossing. We don't have to trace them behind the mirror, which we'll have to do on the next one. I'll show you in a second. We can also find the object distance from the object to the mirror, and the image distance from the mirror to the image. So we choose 3 useful rays. The first one is parallel to the axis, then it bounces off through the focal point. The second one is through the focal point and bounces off parallel to the axis, and the last one hits the mirror at the axis and bounces off at the same angle below as it's traced. Okay, so now we have a convex mirror, but we're going to choose the same 3 useful rays. So we'll have a light ray that goes parallel to the axis. Pardon my freehand drawing. It's hard to use a ruler and a stylus. It's difficult to trace. So in the concave mirror, when the light ray hit, it bounced through the focal point. Well, this doesn't go through the mirror and through the focal point, which is behind the mirror, but it is going to bounce directly away from the focal point. And I can trace that ray backwards behind the mirror indefinitely. The second ray is going to go towards the focal point. So if I drew this ray in a straight line towards the focal point, it's going to bounce off parallel to the axis. And again, I can trace it backwards. And last but not least, I'm going to have a ray that goes to the axis and bounces off with the exact same angle. And I trace that one backwards. And whoa, look at that. They do converge, although they don't actually really converge. These light rays are traveling separate, away from each other, as they bounce off of that mirror. But my eye doesn't understand that. My brain doesn't really comprehend that without, like, just naturally. So I see an image. Even though there isn't a real image produced, the light rays don't actually really cross. I see an image of that arrow behind the mirror. That image is reduced in height, so the height of the image is smaller than the height of the object. It has a magnification less than 1, but it is upright. It's not inverted like on the last example with the concave mirror. It's a virtual image because the light rays don't really cross. It's upright, and it's got a magnification less than 1 because it's smaller than the original object. So what happens when we have an object here, an arrow, in front of a spherical lens? This is a converging lens. Why is it a converging lens? Because when light rays come in, let's say we have a light ray coming in that's parallel to the primary axis, it's going to be going from air out here into maybe glass. Yep, good, I'm still recording. I hit a button. It's going from air into glass. And, or some clear material, could be plastic, but it's going from air into glass, which means it's going to be slowing down. And when it slows down, it bends towards the normal. Up, when it speeds up, and away from the normal. When it slows down, down towards the ground, towards. So when it goes from air to glass, it slows down, it bends towards the normal. The normal of this surface is going to be something like this. Now the light ray wants to keep going through in a straight line, but it doesn't. It bends towards the normal, and then it's going to bend, as it goes from glass into air again, it's going to bend away from the normal, which is going to cause it to bend even farther and go through the focal point. Any light rays coming in and hitting a converging lens like this are going to converge at the focal point on the opposite side. Any rays going through the focal point on this side are going to leave parallel to the axis, and any rays going through the middle of the lens will just continue on in a straight line, unbent, because it's going to go directly in through the normal. And we end up with an image on the other side that is real and inverted. When I have this type of lens, when the middle is a little thinner and the edges are a little fatter, I have an object over here with light rays bouncing off of it. I pick my 3 convenient light rays. The first one is going to go parallel to the primary axis, but unlike the converging lens, is a diverging lens. So the light ray is going to go directly away. It's going to bend away from the focal point. And if you feel compelled, walk yourself through the process of each boundary as the light ray goes from the air into the glass and from the glass back into the air. In both cases, it's going to cause it to bend away from that axis because of the direction of the normal of the curved surface. Feel free to walk yourself through that process. It's worth doing if it helps you understand why it's bending away. The second light ray is going to go from the tip of that object towards the focal point on the other side. And it's going to bend. Before it was going parallel and it went away from the focal point. Now it's going towards the focal point and it's going to bend so that it leaves parallel, but I can trace it backwards. And the last one, just like before, was going to go from the tip to the middle of the lens and just keep going straight through. And that traces backwards to a single converging point. Even though they don't actually converge, they're going, you can see this light ray, and that light ray just continue on indefinitely out into the universe. But they seem to come from a single spot right there, which means we will have an image produced at that spot. That image is virtual. It's got a magnification less than 1 because it's smaller. We can also find from these diagrams, as I've said before, the object distance and the image distance. Okay, so we've talked a lot about how to find the image and the image distance graphically. But that's really ultimately an approximation, because unless you're drawing it exceptionally carefully with precise measurements and precise angles, there's always going to be room for error. Especially, like, I'm doing a pretty decent job with the stylus, I think, but it's not perfect. So what if I want to be more precise? What if I want to mathematically figure out where these images and objects are with relation to each other? Well, then I'm going to use the thin lens equation. It's called the thin lens equation because it only works when the object and image distances are large compared to the width of the lens itself, or otherwise it sort of falls apart. They don't work anymore. We get aberration. So the lenses are relatively thin compared to the object and image distances that we're dealing with. Now, it says thin lens equation. It also works for mirrors. Spherical mirrors still works. Okay. So the equation looks like this. 1 over the focal length equals 1 over S plus 1 over S primed. S is the object distance. S primed is the image distance. One of your labs uses this terminology. Another lab uses different notation. And one of the other, I think the Phet lab uses 1 over P plus 1 over Q. P being the object distance and Q being the image distance. They're the same thing. They just use different terminology. I've actually, in my, I think in my 102 class, my 102 class, I think their book uses a different terminology. They say 1 over dO equals 1 over di. I probably like that terminology the most because it's the object distance, dO, and the image distance, di. Oh, I screwed that up. That should be plus. There we go. All of those mean the same thing. S, P, dO, those all mean the object distance. S primed, Q, di, those are all the image distance. So it doesn't matter what the terminology that you prefer. You can use whichever one you want. I think your textbook and the ray diagram lab both use that terminology. Okay. Magnification. Is the image bigger, smaller? Is it upside down? Is it right side up? We can get all of that from the magnification. And magnification is a ratio of the image height to the object height, or h sub I divided by h sub O. Okay, great. There's another way to calculate magnification as well, and this is really useful because you might not know if the image is bigger or smaller. You might have to just use numbers, and you might not be given the heights. You might just be given where the object and image are, the image distance and the object distance. Well, you can actually calculate the magnification using the image distance and object distance. The magnification is going to equal negative image distance divided by object distance. So magnification equals image height divided by object heights. If the image is bigger, you get a magnification bigger than 1. If the object is bigger, you get a magnification less than 1. You can also get it using the image and object distances. Magnification equals negative image distance divided by object distance.